Audible clearly. Yes, thank you. Welcome to the final Guide to Galaxy session of Horizon for this tenure. I am Abhishek. I will be conducting this session along with Nanta and Asim, and the topic that we are going to talk about is fields to fractals. So we will basically cover a little bit of particle physics and fields, and we will talk about the various problems that occurred when you are considering about fields and how it eventually got resolved. So I will begin this in a slightly different place than what is usual. So we will start from the periodic table of elements. So this is the periodic table of elements, as everyone is very familiar with. It has all the 118 elements that we believe to be the basic building blocks of everything that we see around us. So once you see this, there is something that catches everyone's eye. Basically, if you see the right hand side, it has all the elements, lithium, beryllium, all of them which react very vigorously with water. If we see on the other extreme end, we see elements that are inert and doesn't react much. So you see there are some fundamental properties of elements that are repeating in this periodic table. So this suggests to us about something. These elements are not the building blocks. There is something underlying beneath them that manifests themselves as all this periodicity and symmetry that we see in this table. So this is the thing that you are going to see about in this session. There is something more fundamental, and let us see what it is. So I would like to do some little bit of history behind this field. So this is the planetary Bohr model of the atom, which we all know, we all read about this in school, about how J.J. Thomson discovered the electron, how Rutherford and his gold foil experiment helped to discover the presence of a nucleus, how Chadwick discovered the neutron, and so on. So this was the theory that was proposed by Bohr, that the nucleus is at the center and all electrons revolve around the nucleus in fixed orbits, like how the planets revolve around the sun. So this helped to predict the ionization energy of hydrogen and many other things pretty successfully. But this theory had lots of flaws in it, and this stuff gets more deeper than this. So the thing that I would like to talk about now is cosmic rays. So cosmic rays are particles, high energy particles that originate from outer space. So once they have their origins outer space, and then they enter the Earth's atmosphere. And once they enter Earth's atmosphere, they interact with the particles in the Earth's atmosphere, and that produces much more particles. So why cosmic rays? Because they are before particle accelerators, we didn't have access to that high energies that was required to find new particles, and these cosmic rays was a very helpful mechanism by which we were able to figure out a lot more about many elementary particles. So our story brings us to this guy, Carl Anderson, this diagram, and this instrument. This instrument is called the cloud chamber, and the thing about this instrument is that when a charged particle passes through this cloud chamber, it leaves behind a path of ionized gases. So around these ionized gases, little droplets condense, which forms a cloud-like trail. So what this helps us to do is, say a particle passes through this cloud chamber, it leaves a trail that makes this particle's path visible to a naked eye. So this piece of equipment was very, very useful in the earlier days of particle physics, and Carl Anderson was experimenting with this, and then he figured out a lot of stuff. So before we go into that, a couple of points about this cloud chamber. It has a huge magnetic field in it, which helps to bend the particles that enter this cloud chamber. So how is this helpful? Basically, when a particle enters this cloud chamber and it bends, we can calculate by the degree of its bend its charge to mass ratio. So this will be helpful in finding the properties of the particle. The second thing is that this particle had a lead covering placed, so that the chamber had a lead covering placed, so that the particles entering it will lose some energy going through that lead, which makes these curves more tighter, so that you can very easily figure out E by M ratio with more accuracy. So this was the trail that he observed. You can see there is a little bit of a curve here that you can observe. So the interesting thing about this curve is that this is the exact curve that an electron would have taken inside this cloud chamber, but with one difference, that it is bending in the opposite direction to which an electron would have taken. So you would have you would have thought that this is a proton probably, it's a positively charged particle, so it bends in the other direction. But since it bends in the exact way of an electron, so basically you know that its charge to mass ratio is the same as an electron, but in the opposite direction, basically the opposite charge. So this was the first experimental observation of a positron, which was an antimatter particle. So this is one of the first indications that whatever we thought were the elementary building blocks of this universe were not really the complete picture that we had, and there was more stuff to it. So the second part we come to this story is a story about a new force. So all of us know about the Rutherford's gold foil experiment. So in the gold foil experiment, basically you have alpha particles hit towards the gold nucleus, and then some of them, due to the interaction with the gold nucleus, they rebound, scatter. So but the thing is, while this helped to predict the presence of a nuclear, the theory itself had some holes and flaws that were not explained at that time. The mass of the gold nucleus is much higher than the mass of an alpha particle, about 80 times higher. So basically what that means is that this the Coulomb repulsion between the nucleus and the alpha particle should have been much lesser than what they observed at that time. So basically at that time, whatever theory that they had predicted that this alpha particle should approach the gold foil nucleus much closer than what it actually does. But this is not what was observed experimentally, which was obviously not explained by theory. In retrospect, it is easier to just say that there is a new force, there is an other force apart from the Coulomb's force inside the nucleus that causes this. But the scientific community at that time were not yet ready for a proposal so bold like a new force. So like Rutherford originally suggested that this effect could be explained by some deformation in the alpha particle itself, but such explanations and many more proposed by various other scientists proved to be increasingly untenable as more and more experimental data piled up. So in the end, finally, at a meeting in Royal Society in the year 1929, Rutherford clearly stated that the hydrogen and helium nucleus appears to be surrounded by a field of force of unknown origin. So this is a huge thing. So basically he admits that in whatever theory we have is incomplete, there is something that we do not know of. Now the task before all the scientists at that time, both experimentalists and theorists, was to come up with an explanation for this new force. So the major breakthrough came in 1934 by the Japanese physicist Hideki Yukawa. What he stated was the following: say there exists a particle of mass m and spin 0. I will not go deeper into what exactly the math he came to arrive at this, but what he stated is basically a particle of this property, if it existed, it will give rise to a potential energy, and you know potential energy is related to the force. So a potential energy between the particles that varies with distance as the following. So potential basically varies with distance as this. So this is now called as the Yukawa potential. So the interesting thing about this potential is that it has the property that it goes to 0 very quickly for values of r much greater than capital R, where capital R is the range of this unknown force that we are trying to figure out. So at that time we had experimental data for the value of capital R, and Yukawa basically figured out the relation between this capital R and the mass of this particle. So he found that they are inversely related by the following relation. So what he says is that for the experimentally observed values of capital R, there should be a particle of mass about 200 times the mass of an electron. So he says that if such a particle is found, it can easily explain this discrepancy we observe in the gold foil experiment. This theory languished for some time until the year 1937, when such a particle was actually found. This particle was named meson. So we will reach another point in our story. A minor note that we are not exactly growing in chronological order. I am just picking up stuff that I found interesting in the history. So yeah, about beta decay and the for discovery of the neutrino. So yeah, beta decay at that time was just thought to be the release of electrons from an atom. They didn't fully understand what it was. So the discrepancy, the problem with beta decay was compared to something like alpha radiation, beta radiation didn't have a fixed energy that they could observe. Say alpha radiation, you make alpha radiation by a process, you put in some energy E, and then you get out alpha particles of the same energy E, basically by law of conservation of energy. So some similar thing that people expected, that beta rays also, whatever energy that you are putting in to produce these beta rays should be the same thing that comes out. But that is not what happens. You instead get a continuous spectrum of energies for these beta rays. So this was a problem, and Niels Bohr, being as courageous as he always was, wanted to ditch energy conservation to explain this phenomenon. But Wolfgang Pauli, however, had different ideas. So what Wolfgang Pauli suggested in his very famous paper that he wrote, a letter that he wrote to a conference, which he titled "Dear Radioactive Ladies and Gentlemen," he says the following: say in beta radiation, apart from the electron, there exists another particle, a neutral particle, that we are still not detected. So what he says is that the energy of this beta radiation basically gets split between this new particle that we are not able to detect and the electron. So this explains how the electron's energy is continued. So basically, say the sum of this energy of this neutral particle and the electron will be the same, it will be fixed. But since we are not able to detect this new particle, the only particle that we are able to detect is the electron, and thus the electron, we measure the electron's energy and it has various values. So this explains the discrepancy and it doesn't violate the law of conservation of energy. But Pauli was at that time very nervous about his proposal. This particle was later named the neutrino. So he was at that time very nervous about this proposal. Indeed, in his original letter, he says that he doesn't feel secure enough to publish anything about this idea yet. So now that this particle was proposed, the task was detection of this particle. So why this particle was very difficult to detect was the fact that it doesn't interact with other particles very easily. Theory at that time suggests that for this neutrino to interact with something like say lead, one single neutrino to register one interaction with lead, it has to travel almost a light year through it. So it is very improbable that it ever interacts. So the resolution to this problem is not to focus on a single neutrino, and instead you go to a place where there are many neutrinos. So you set up an experiment, they set up their experiment in a Savannah reactor site, which is in South Carolina, USA. So yeah, so beta decay is basically the decay of neutron to give proton, electron and a neutrino. So the inverse process is also possible, in which this neutrino will combine with the proton to give positrons, which are the opposite charged particle for electron that we talked about earlier. So this positron, when it meets an electron, it will annihilate and then it will produce gamma rays. So why these gamma rays are very useful is the fact that they are like a signature for the presence of neutron. Signature of a neutrino, sorry. So whenever a neutrino gets released, there will be like two pulses of gamma rays that can be easily detected, and this is experimental evidence for the presence of a neutrino. So once this experiment was conducted, they actually did observe various pulses of gamma rays. So this major discovery at that time was, to announce it, was an exciting and nerve-wracking thing for the scientist. But on June 14th of 1956, Cowan and Renes, who did this experiment, sent a telegram to Pauli that read the following. They said in the telegram that we are happy to inform you that we definitely detected neutrinos from fission fragments by observing the inverse beta decay of protons. So interestingly, Pauli's reply was never sent to this. It only was found in his papers and letters, and it read as thanks for the message, everything comes to him, for who knows how to wait. So I would like to conclude my historical interlude with this quote. Basically, years of theory, experiment and lots of patience was put behind discovering many of these elementary particles. And finally, this is the current standard model of elementary physics, and these are the particles. So you can observe two classes of particles in this basically. The first class is called fermions. So fermions are the stuff that makes all the matter that we see around us. So fermions are of two types, one is quarks and other is leptons. So up and down are the first generation of quarks, and electron neutrino are the first generation of leptons. Together these make up everything that we see around us. So, and then you might wonder what the second and third generation of particles are. So basically, for some reason that we still don't understand fully, there exist particles with the same properties of the first generation of particles, but with higher mass. So these particles are very unstable, and they are only formed in our reactors and stuff, and they quickly decay to the first generation of particles. So that constitutes the second and third generation of quarks and leptons. So these are fermions, and then there is a second class of particles called bosons. So these particles are the ones that carry interactions between these matter particles. So if I have, say, our earth and sun interact, or me and this mic is interacting or something, these all require forces, and we all know the major forces in the universe, which is gravity, electromagnetism, strong nuclear force and weak nuclear force. So the interaction particles help us to explain three of the four fundamental forces. We still haven't found the fundamental particle that carries the force of gravity, so that is not there, but gluon is the particle that carries the strong nuclear force, photon is the particle that carries electromagnetic force, and W and Z photon are particles that carry the weak nuclear force. And finally, there also exists this particle called Higgs boson. So Higgs boson is quite famous because it was discovered recently, and it helps to explain how particles get their property called mass. So basically, interactions with this Higgs particle is what gives other particles their property called mass. So this is a very brief and simplistic summary of the standard model. So while it is an elegant theory, surprisingly the best theories about the universe that we have currently does not even include particles. So then you might ask, what exactly does it include then? The best theories about the universe that we have right now is about fields. So why? So there are many reasons for why we prefer fields rather than particles, and I will list some of them. First and importantly, fields allow us to preserve our sense of locality. What do I mean by this? Basically, we all know, like from Einstein's theory of relativity, that the maximum speed at which information can travel in the universe is the speed of light. So say a particle is wiggling here, according to the Coulomb's law, this wiggle should cause instantaneous changes to other particles that are millions of light years away. But that violates this principle of locality, and fields give us an elegant way to account for it, in which fields are the ones that carry this information about this particle's movement from this place to other place, and thus the information travel doesn't happen instantaneously, and we will be able to retain locality. That is one point. The second consequence of fields is that all particles of a given type are the same. So a particle that is produced in a particle accelerator here, and a particle that is produced millions of light years by interstellar process, say a supernova or something, is completely identical. So this seems counterintuitive to us, because we feel like the process in which the particle is made should have some effect on the particle, but that doesn't happen. Fields provide us this explanation that fields are something that permeate throughout space, and they are same throughout. So since the particles are something that manifest from this field, since the field is the same, the particles also should be identical. One more reason why fields are an elegant way to think about all the processes is that it allows us to interpret situations where the number of particles changes. See, even in the beta decay that we saw before, a neutron will decay into give so many particles. But then if you think only in the sense of a particle, it implies that the neutron was made up of this particle, or these particles somehow existed inside the neutron, which are not accurate. While fields basically will provide a better way to think about this, in the sense that each of this particle is just a ripple in this field, and there will be multiple ripples that will cause more particles to manifest. So fields allow us to interpret the situations in which number of particles changes in a more elegant way. So what exactly are these fields, and how exactly to mathematically formulate them, my friend Nanda will take over from here. Thank you.
Yeah. So why fields? So for people, like, that's just a meme. I don't know how to explain the meme to you, but basically there's this craze with quant, right? People in Insta love quant and stuff like that, and generally people would be like mathematics, people who are good at math and physics are considered to be like not doing physics anymore and just jumping into quant. This is just a reference for them, but whatever. So let's take a step back. Yeah, so let's take a step back and think in terms of let's just be kids for a minute. Now, I know the existence of an electron. I know what an electron is. At least I think I do. Let's say, and then I know what a photon is. At least I think I do. Now, in some cases, in some situations, basically I know that let's say a high school student would know that an electron and a photon has wave-like nature in some situations. Now, that seems to imply that these two have some similarity with them, right? They sound like they have some commonality in them. Now, but classically, let's say you what? Yeah, one second. Yeah. So classically, let's say, what's an electron? Can someone just explain what an electron is? At least what do you think an electron is?
It's a small negatively charged particle with a certain mass.
Okay, so electron is a negatively charged elementary particle. And what do you think photon is?
Massless elementary particle, which has no charge either. It's a particle that moves around.
Okay, so if you have some idea of electromagnetism, that's the saying that basically for light or photons are just excitations in my, or waves in my electromagnetic field. Now, that's interesting, but then again, what's more fundamental is what I'm trying to motivate here using this very dubious sounding argument. But basically my point is, are particles more fundamental, and then in some classical limit, let's say field emerges, or are fields more fundamental, and then in some limit I get particles? What do you think is more fundamental? I'll just give you the answer. Particles are not more fundamental, and then fields are more fundamental. Why is what I'll try to motivate in a good 45 minutes, I guess. So before going to all that, so Abhishek said something about locality, and then how physics is local. Now, okay, so what do I mean by that? So he said that basically in my Coulomb's force, I assume instantaneous propagation of information, which I know is not true because it violates principles of special relativity. So what does special relativity say? It says my laws of physics should be invariant, and it says that the speed it puts an upper bound on the speed in which my information can propagate, which being speed of light. Now, it seems like classical mechanics is not compatible with the formulation of special relativity. Now, for someone who knows SR to some extent, would probably be like, we have relativistic kinematics and stuff like that, right? So that I basically understand particle collisions or stuff like that in a even with imposing what SR demands me to do. Now, but if you think about it, I know the particle's kinematics, sure, in a relativistic setting, but do I know something of interactions between multiple particles? Does my relativistic kinematics tell something about that? The answer is no, it does not. So that is one reason why you would need fields. But then again, before knowing why do I need fields, I first have to understand what a field is. And yeah, so what is a field? Can someone answer what a field is? What do you think a field is?
Mathematical object assigned to space-time coordinates.
Yeah, so okay, so so let's say you have you have any mathematical object, it can be a scalar, vector or a tensor, and then I assign unique I assign at each point in my spacetime such unique objects, and this basically is what a field is in physics at least. So that brings me to another funny meme, and the clarity is quite bad, I believe. Yep. So what that meme basically says is, so there's this concept of fields in mathematics, which I believe at least is not as useful or as useful as what or in the way in which fields are defined in physics. I basically say that what I'm trying to say is physics, the concept of fields in physics is better. Like math, you just deal with rings, stuff like that. That's not interesting. So yeah, that's just a meme. So yeah, now so that is how I defined. So I can basically, so that's a definition of a field, I guess. But before that, let's look into. I'll just give a quick 101 of what SR says. So basically, any theory in physics, let's say, revolves or lives in a background space, right? So in classical mechanics, the theory of classical mechanics basically lives or deals with spaces called affine spaces. What is an affine space basically? It's just, in layman terms, it's just your Euclidean space of n dimensions with no specific choice of origin, or there is no preferred origin. That's the main difference. Now, this sounds weird, but it is physically true, and you can easily see it. So, does physics or laws of physics care about origin or some preferred point in classical mechanics, in the settings of classical mechanics at least? No, it does not. So yeah, so that being said, this space in which my theory lives or revolves around has some structure or has some properties, fundamental properties inbuilt on the background space itself. So yeah, you can think of it as you can think of it in a geometric sense. Now, these are some things which we call as space-time symmetries in SR, but symmetries of my background space. Now, I'll just name or list out the symmetries that I get in SR, and I will, I'll try to motivate them. So, the first one which you have is, so does anyone know what this is? What I'm trying to say? Okay, translation symmetry, as someone here pointed out. So translation symmetry basically means my laws of physics don't care where I conduct my experiments in a way. This is a way which is easy to understand. So yeah, so this is one symmetry, and obviously based on my number of dimensions, there are 3 such coordinates. That's fine. what's another class of symmetry that this background space has, or I am saying it has? It's a claim. You can think of it as a claim. I am putting it as a claim now. So, does anyone know what this means? Okay, what is a rotation? Does anyone know what rotations is? What rotations are?
A change in orientation without change in length.
Okay. Okay. Think in terms of vectors or yeah. So
It's a transformation that doesn't affect how large a vector is or its magnitude.
okay. So yeah. So it's basically a linear transformation which preserves my 2 norm. What is my 2 norm? Euclidean distance. Pythagoras theorem for people who Pythagoras theorem. So yeah. So this R is basically a group of symmetry which is represented via matrices on my space R3, sure. So what it basically does is it preserves my 2 norm, which is Pythagoras theorem. Done. So this is one symmetry that I have, which basically in layman terms, what does it say? The orientation in which I conduct my experiments don't matter. Fine. So what is an inertial frame? Does anyone know what an inertial frame is? I mean, it will be boring. It might sound boring and slow because there are prerequisites to it. We won't be able to cover everything, but I'll try to explain something at least. So yeah, what's an inertial frame? Can someone answer? Or I'll just answer, it's fine. Okay. So what an inertial frame is that? So 2 frames that are related to each other via linear transformation that basically preserves the laws of physics in them, or the form of laws of physics in them. So another way is that 2 uniformly moving frames with zero acceleration, constant velocity. This is okay. So if you on top of this, if you assume my time in all these 2 frames is same, or time is absolute, you basically end up with a restricted class of linear transformations called my Galilean boosts. Boost is just a fancy word, it's just a linear transformation. Now, since it's not a lecture on SR, this symmetry does not hold in my in special relativistic settings. So what I do is I basically assume that time is no longer absolute. Time and space are in equal footing. This word equal footing is quite important. I might be using this multiple times. So I assume time and space to be in equal footing, as in they can mix with each other and via linear transformations. So I'm proposing a linear transformation to you, which basically ensures that, which basically satisfies what a symmetry is, which basically is to make sure that my laws of physics, at least a form of my laws of physics, are invariant under such coordinate systems that I construct. So this is I hope you can see this. I just wrote Lorentz boosts in using matrices, but so if you want to know more about it, just figure it out. I just get to know about it, do your homework. But basically, this is a more general class of linear transformations than my Galilean transformation, which makes sure, while imposing the 2 fundamental postulates of special relativity, my laws of physics behave the same. So in inertial frames, this just defines a connection between inertial frames by imposing my fundamental postulates of laws of physics. Also, you can think of it as hyperbolic rotations that basically, okay, so fine. Someone mentioned this rotation is basically a transformation that preserves my 2 norm. Can I construct a norm, or can I construct a invariant or norm which basically ensures that for which basically remains invariant under this proposed transformation. So there is such a norm which is called by Minkowski metric norm. Yeah. So I won't be talking too much about it, but this is basically the background. This basically talks or is the description of the background space in which I do SR. Minkowski metric is very fundamental, kind of fundamental. Fine. Okay. So why did I do all this? To make you understand the problem. Classical mechanics is not compatible with SR. Interactions, that too, can't be explained even with relativistic kinematics. So what do? How do I construct a theory which basically incorporates all these principles, makes sure my SR is valid, a theory which basically reconciles SR and special relativistic interactions, basically classical interactions, quantum interactions. So such a theory, okay, so now I'm proposing another claim that the concept of fields or using fields is the most simplest mathematical structure you can use to reconcile all these issues that we currently faced. So yeah, this is a claim. You can look it up if you want. But yeah, now how does this fields fix this mathematically? What are fields? Now let's go back to my classical mechanics for a minute. Let's take a small detour. So what is a state? Can someone explain me what a state is? Okay, so I'll just say, okay, so basically state is the minimum number of, in layman terms, state is the minimum number of labelings and informations that you need to uniquely classify a particular system's configuration at some parameters, let's say. So these parameters being t and t here, so at some point in time, so that is basically what a state is. Now in classical mechanics, usually I define my state using x and p, position and conjugate momentum. Now this is finite. I can have 2n states, I can have 2n elements in my states, which is still a finite number. Fine. Now I am proposing you fields. Okay, so I earlier said that I treat x and t in special relativity. I basically have to treat x and t equally in some sense. Now what my field does is, so this is another proposal that I am giving you. Try to see if it makes sense. So I now define my states using a function which takes both x and t as parameters. Here if you looked at this, x and t are not parameters. T is a parameter, x is not. Now here I basically have a function which takes x and t as parameters. Now, so this, and it has a conjugate momentum, let's say. Fine. Okay, I'll have to go. Fine. This basically gives my state in my field theory. Now what do they even mean? Okay, so before that, can someone guess the degrees of freedom I have in this list? Or can someone guess how much items in my listing do I need to properly explain or properly define my state? Can someone take a guess? Do you think it will be finite, infinite, uncountably infinite, countably infinite?
Countably infinite.
Why do you think so?
Well, you're contrasting this with particle theories, which are finite. So So in this case, it's obviously infinite, but it's uncountably infinite. We can't do much with it. So countably.
Okay. Why do you think we can't do much with it?
Because I've never seen anything.
Okay. So it has uncountably infinite listings, elements in this list. So simple ways to think about is fix x. So I need to have at least one degree of freedom when I fix x, right? Like, so this a is a parameter. So it says at blah blah blah. So a keeps going on. So minimum case, let's say fix x, I have at least one degree of freedom. Now x is something that continuously varies. It belongs to your real numbers, which are, so I will get uncountably infinite number of things in my state. Sure. So I would need, so basically what I'm saying is I now have infinite degrees of freedom, which are again not countable. So yeah, we are assuming only two types of infinities exist, by the way. So if there's anyone who knows math, please don't come and kill me. So yeah, that's there. What else is there? Okay, so okay, that sounded interesting, I guess. But now, is there, okay, so if someone attended a session which was conducted by me on Valentine's Day, okay, so I basically talked about dynamical systems and manifolds, where I posed a question like, so let's say okay, so if I have a finite dimensional state space, okay, so in layman terms, ODEs have something to do with finite dimensional vector spaces. Can I have infinite dimensional state spaces or vector spaces, and can I have a corresponding operator associated to it? In some sense, this is not mathematically rigorous, please don't kill me. So do you think I can have such an associated operator to it? You guys would have seen it multiple times, I'm pretty sure. What is that?
In quantum mechanics.
I mean, it's used in quantum mechanics. It's an operator. It's very similar to my, okay, it's very similar to my differential.
Momentum.
It's very similar to ODEs. Yep. Someone said the answer. Partial differential equations. So, what is a partial differential equation? It's an operator that lives in an infinite dimensional Hilbert space. What is a Hilbert space? I'm not gonna do homework. Basically, I'm not gonna explain that. Out of scope of this. No, it's not an interest also here. I mean, it is an interest, but out of scope. So yeah, fine. So what the point I was trying to make here is a very non-rigorous argument that what's the natural mathematical language of describing such items? What do you think is? How can you define such items in a math using math? What I was trying to just show the correlation or connection here. So PDEs are the mathematical way of describing about such fields. Now, let me pose you another question. Do you think fields need to have dynamics involved in them? Dynamics meaning just varying with time, obviously, because interactions are dynamic in nature. So yeah, so all the dynamics of my fields are governed by a set of partial differential equations, basically. So okay, let's take a step back and look at the history for a minute. It's very funny that the idea of fields was first proposed long back, before people even understood its significance or how its importance, basically. What do you think was the first kind of fields that were proposed in physics? You guys would obviously have heard about it. Yes, Faraday, I believe, proposed the idea of electric fields. I mean, so let's say I know nothing about physics. Two magnets with no one pulling, they just move. Feels like magic to me. So, yeah. So to explain such interactions, fields, the idea of fields was proposed. Yeah. So EM fields was proposed. EM fields when they proposed, and then Maxwell obviously wrote down a set of famous equations that governs the dynamics of my EM field. And the funny part is, people did not understand the importance of SR or my fields in general, and then the issue or the discussion of SR first developed because they found inconsistencies with classical mechanics and electrodynamics. So basically my Maxwell's equations are not invariant under Galilean transformations, they are invariant under Lorentz transformations, because now I have just motivated that fields are something that are consistent with SR. So you would expect it to follow the set of symmetries that my special theory of relativity has inbuilt into it. And yeah, so basically that led to the whole discussion of development of SR, which is pretty interesting. Fine. Now, yeah, so let me just write Maxwell's equations for what gibberish did I write? This gibberish is called Maxwell's equations. Now, people would most probably be familiar with the four sets of equations involving curl and divergence. This thing is a more compact form of writing it. Again, look it up. This thing basically has this thing is basically Maxwell's equations written in a different form. It's just jargon. It's not that big of a deal. So, yeah. Since it's not SR, we won't be covering on what these are. I'm just saying these are partial differential equations that govern the dynamics of my field. So yeah, now there's another type of fields in classical settings itself. Can you think of such? Magnetic fields. I'm not gonna be talking about magnetic fields. So, yeah, moving on. I proposed a bold claim in the beginning that fields are more fundamental than particles. Now, classical theories, I've seen that fields are, seems like a much more better description of what's going on. But for something to be truly fundamental, I would expect it to behave well with all laws of physics, right? Multiple domains of physics, right? So particles, what does the word particle trigger in your mind? It should trigger the word quantum mechanics, at least, I hope. So yeah, now so in quantum mechanics, what is quantum mechanics? Can someone answer what quantum mechanics is? Or at least, I won't expect anyone to know quantum mechanics. Just propose what makes quantum mechanics different from classical mechanics. Some points, some radical ideas.
Forces energy to be quantized. You can't take every value of energy.
Okay, so yeah, quantization of energy is one such idea. There are a few radical ideas. And I'll just take a small detour and explain something about, or at least try to explain something about quantum mechanics. So, in quantum mechanics, I basically have an imaginary wave function which lives in a Hilbert space, and then this thing has information about particles evolution and not particle solution, yeah, okay, particle solution, particles time evolution, and then the probability of it being found somewhere, blah blah, fine. So I have what I'm saying is I have a PDE, let's say, which defines the dynamics of such a theory, my Schrödinger's equation, non-relativistics, just take note of that. Plus I have some funky quantities like wave functions, blah blah, whatever. So one main thing about quantum mechanics is that I have seen x and p in classical mechanics, position and conjugate momentum. These now are operators in Hilbert space. What does this mean? So so I'm just gonna give one over and I'm not gonna explain what a Hilbert space is, what wave functions are. So let's say there's something called a wave function which lives in a Hilbert space, which is a abstract space. Now operators or mathematical objects that live in my Hilbert space, these things act on my wave function and then give out something which I can physically observe, which I call as observables. So so what I'm trying to motivate here is that even though these things are look abstract and live in an abstract space, these things are intricately tied to what I observe in real life, observables. So now x and t's are operators, but it's x and p, my bad. So t, obviously dynamics, I have said that my Schrödinger's equation governs the dynamics of my of this theory or of this system, right? So obviously there should be time evolution. Here t is a parameter. Okay, this is non-relativistic QM. Can someone propose, okay, so do you think non-relativistic QM is useful first of all in high energy physics or high energy stuff with high energies? Do you think non-relativistic QM is useful? I'm gonna give you an answer. I'll just give you the answer. No, it's not. So you need, because particles will be moving, let's say there are particles will be moving with speeds very close to light, right? So obviously you will expect SR to play a decent role. So I need a theory which basically is consistent with the principles of quantum mechanics, the ideas of quantum mechanics, and my SR, good old SR. So how do you do this? So naively, if someone has done something related to SR in classical settings, you would most probably be like, bro, just change the Lagrangian in my action with some change the form of my Lagrangian such that it satisfies my principles of SR. You'll be like, just do that. Can you do that? So I have in my Schrödinger's equation I have Hamiltonians, right? So what is Hamiltonian? What is Lagrangian? Good question. If you don't know that, please do your homework. Hope it's visible. This is Schrödinger's equation. At least I believe it is. So, yep. This H is called a Hamiltonian, which is an operator in my Hilbert space, obviously. Now, okay, so can I just replace this H, like in classical mechanics I said, just replace the Lagrangian. Okay, by the way, there's a connection between Lagrangian and Hamiltonian, just take that as a fact if you don't know. Can I just do some modifications to my Hamiltonian to get a relativistic theory? Do you think it's possible? Or is it that simple? Obviously it's not that simple, but why do you think it's not that simple? Any ideas? Okay, by the way, the motivation of this session is not to explain anything, it's just to give you more doubts. So that you actually know that there are some stuff that is weird and then try to understand it. Don't take everything for granted is the main philosophical motivation of this whole session. So yeah, where was I? Yep. Okay, so is it that simple to get a relativistic theory for Q? Nope. Because again, take this as a fact if you don't know SR to a good extent. E is not p square by 2m anymore. Simple words, in simple words. This also I assume c to be 1, speed of light to be 1. Sounds very weird. In SR we basically use stuff called natural units where we set c to be 1. It's something physicists do in SR, so why not just do it here also. So this is a result in SR. So also my operator P has this form for people who don't know. You don't need to understand it properly. Or okay, I hope it's visible. If it's not visible, please let me know. Now get a Hamiltonian. Let's say the Hamiltonian for in this case is does this make any sense? It does not make any sense to me. So there is one issue. There is one issue here where I can just trivially, modify my Hamiltonian to satisfy SR relation, like incorporate SR into it. I have to do something much more, rigorous or much more elegant. It is elegant, but much more important. So earlier I said that I'll be using this phase where in SR treats x and t to be in same footing in some sense. Basically, quantum mechanics treats t as a parameter, x as a operator. These two are completely different things in quantum mechanics, right? The descriptions are different, but SR forces or wants me to assume these to be same in some sense. Now I have two options. I can either promote t to be also a operator in my Hilbert space, or I can treat x to be a parameter. These two options sounds like something. It sounds logical, right? I can do either of these. I end up doing only one of these things because the other one breaks or is in conflicts some other regions of physics. Again, I won't be explaining what exactly goes wrong when I do that. If you are interested, do look it up. Now what is the correct way of doing this? That apparently is to parameterize x instead of promoting t to be an operator in Hilbert space. This leads to some issues. Okay, so now that is fine. Let's think of our motivation first. I need a QM. It's not okay. 1 second. Duster. Sharp. Okay, so there's no duster sadly. Oh, there is duster, not sadly. Fine. I forgot what I wanted to say, but that's right, I guess. Can someone remind me what I was saying? Or did I lose you guys? It's fine if I lost you. Okay. So let's take a step back and look at what we're actually trying to do. QM is not compatible with SR. I want a theory that is compatible with SR. I know fields are compatible with SR. So if I can somehow construct a theory which involves fields in quantum mechanics, I get a theory which is compatible with SR. Transitive property for people who are who like say theory or whatever. Transitive, bro. Fine. So yeah. So it seems like I can just construct a theory using fields for quantum mechanics, and since fields themselves are consistent with SR, I would get a consistent theory for quantum mechanics which is also consistent with SR. Fine. So, and also if you think about it in fields, we just parameterize x and t, right? We treat these as parameters. So, yeah. Why don't we do the other approach? Is just figure out, just search, look it up. I'm not going to explain it. So, now, one important thing that quantum mechanics enforces onto one radical thought that quantum mechanics has that's very different from classical mechanics is that position and moment, uncertainty principle, position and momentum have inherent uncertainty built into it. Now, Heisenberg's uncertainty principle. Now, there's an interesting way of expressing it. I'll explain what it is. This is basically uncertainty principle in some sense, I would say. Now, what is this? I'll try to explain. X and P operators in my Hilbert space. What is a Hilbert space? Figure it out. So, what are these brackets? Do you know what these brackets are? Are they mathematical? Are they some operation, mathematical operation, whatever? Or are they just, I just don't like curly brackets, I'm putting box brackets. Commutator. What is a commutator? What do you think a commutator is?
Checks whether the two operators in question commute, and if they don't, what's the value. So effectively, if you apply the first and then the second, is it the same as applying the second and then the first?
Yeah, it basically verifies commutativity and then checks if the order in which I apply my operation matters. I can say these things measure the failure of commutativity or how much these two operators fail to commute, or the flows that these operators generate fail to commute. Now, what is a flow? I'll try to explain, but if you attended love dynamics, you would most probably have a decent idea of what a flow is. It's just a group action, bro. What is a group action? Figure out. So, yeah. Group action of time on whatever. Fine. Okay, so mathematically, let's say I have two operators. This basically measures failure of commutativity. If both operators commute, these two are same, 0. Interestingly, x and p do not commute, and then I get some finite value. So this basically says the order in which I apply my x and p operators matter. Now this basically encodes uncertainty. In classical mechanics, I have a similar object called my Poisson bracket, which at least I think it is. Okay, it is. Yeah, my memory is quite bad, but yeah. So yes. So this has uncertainty built. So this is basically uncertainty principle. This is one radical thing that QM proposed. So my fields till now are all classical in nature. If I want to build a quantum theory, how do you think I would? What modifications do you think I should do to my field to get a quantum theory using that field? How do I quantize the field? How do you think I should? What do you think I should do? It has something to do with commutators, by the way. Can someone take a guess? Very simple. Just just impose this non-commutativity of x and p operators to my states in classical field theory, which is phi and pi of x comma t. And what I'm trying to do is basically promote these functions as operator valued functions. Now, and then I impose this onto them. So what I'll do is phi of x comma t, pi of a comma x t. I mean, it does not matter, but fine. Okay. I have quantized my field. Basically, yeah, so now I can use fields in quantum field theory. This basically gives rise to a theory which is consistent with SR, it's consistent with QM, quantum field theory. So, yep. This is called second quantization, I guess. Second, first, yeah, second. Yeah, okay. So, yeah, very interesting, but fine. Let's take a step back. Let's take a step back and then discuss about Lagrangians. Or these things are pretty common in classical mechanics, right? I think 1010 has Lagrangians. So, no, not this. 1 second. Can I construct Lagrangians for fields in some way using fields by taking these functions as my states, classical by the way. So can I do something? Can I construct a Lagrangian? I can. Why not? Okay. Yeah, I can construct an action principle for that matter. Why did I write d power 4x instead of d cube x? Yes, and again I am putting out a claim for at this point in time that this object is Lorentz invariant. That Poincare invariant, but fine, Lorentz invariant same. So what is Lorentz? What is Lorentz invariance, or what is Poincare invariance for that matter? So I saw some set of symmetries in my SR, right? Those things basically form a group. What is group is? I'm not going to explain what a group is. Okay, fine. They form a group. Now, so how much parameters are, I erased it, but it basically forms a 10 parameter group called my Poincare group, which basically has 4 continuous symmetries, 4 translation symmetries, 3 rotation, 3 boosts. Yeah, so that thing basically is a complete symmetry group of SR. So this theory, since I say it's compatible with SR, should be compatible with the symmetry group, or those symmetries should still hold. So all my dynamics, I can get dynamics out of this quantity, right, by using variational principle. If you don't know what variational principle is, figure it out. I hope everyone knows what a Lagrange equation is, at least. So yeah, usually it's called Lagrangian field density, but I'll just call it Lagrangian for fields. Lagrangian for fields. So yeah, now for all the dynamics that I can get from this thing, for them to be invariant with SR, this thing should be a Poincare invariant thing. Yeah, sure, why not? So yeah, for this to be invariant for this to be a Poincare invariant, this thing should be Poincare. This thing should also be a Poincare invariant object. I said a claim that this thing is invariant. Now, which means my Lagrangian that I construct should also be at least made up of multiple parts, let's say A, B, C, and each of these things should be individually a Poincare invariant. Makes sense. I mean, need not always be the case. It's just a restricted class of such conventions, I think. Yes. So, yep. What I'm basically telling you is how to choose a Lagrangian for a field. Just these are some minimal conditions that you have to impose. So, yep. Now, when I detour over. Now let's go back to my relativistic QM. So, how can I construct a relativistic QM now? One naive proposal was time and space as one naive proposal that I can give is treat time and space to be same. This kind of means that my equation or that my law of physics should treat them to be similar in some sense. and in starting this equation I have a first order linear operator for time and then a second order linear operator for space. Why not just have both as second order? Some guy, this is a very vague, very sus way of saying it, but there are deeper reasons as to why formulation for the formulation that I'm about to show was proposed for being a candidate for relativistic QM, which failed for some reasons, which I will try to explain at least one of them. So whatever, I mean, this is just a form of the equation, just yeah. So this class of equations are called Klein-Gordon equations. This is another way of writing it for people who like EMT, or for people who know this is called a D'Alembertian. It's just a jargon no one cares. So yeah, this is one such theory which was proposed. Now this failed because if you go back, I said E square is P square plus M square, right? Setting C1 in SR, as far as SR is concerned. So this positive values make sense. Now this thing, okay, this is a claim, sure, take it as a claim. This thing solves this, or this thing is compatible with this in some sense. Now the issue is, this thing has both plus and minus components to it. Now the issue with this is that I can't now define a ground state properly. Why? Because P can take any positive values. Yes sir, as far as S is concerned. And yeah, because E square minus P square is an invariant quantity, so it can take any positive values, let's say. Now this thing gives me, basically can give me infinite energy, negative energy, whatever. Some funky business is going on. There's no proper defined ground state. Now this is one such reason why this thing was discarded. Okay, wait. So ground state has some energy. This is supposed thing, but it's a there's no, obviously it's not a video, so it's static. You can just treat it as static. Euler-Lagrange equations for people so Euler-Lagrange equations for field. This is my Klein-Gordon's equation of motions that I get from Klein-Gordon's equation. Like just I have a Lagrangian for my Klein-Gordon's equation formulation, whatever. Just substituting that and that, you'll just get this in layman terms. So yeah, moving on. Memes. QFT, spoiler alert, QFT. If a mathematician sees QFT, he'll be very pissed off, because QFT does some complete mathematical atrocities, such as infinity minus infinity is equal to a finite value. Stuff like this. Makes sense? It does not make sense for me. So yeah. Now let's construct. Okay, so let's constrain ourselves to a specific class of fields, like which toy model of fields which are easy to deal with. Now I have infinite degrees of freedom, right, for my fields. Now let's say I need a field whose dynamics associated with each of my degrees of freedom evolve independently of each other, of other degrees of freedom. The degrees of freedom's time evolution is independent of others. That's what I'm trying to say. Let me just consider fields like this. These kind of fields are called effective field theories. Nope. Free field theories. Yes. Now, what's the use of this? Is that it's much more easy to play around or show where things go wrong, and why quantum field theory has a lot of such things in it, feels sus. So yeah, so one second. Yeah. So quantum field. Okay. So wait, where was I? Great. Can someone remind me what I was trying to do?
The ground state energy was infinite.
Okay. Yeah, I was talking about free field theories. Okay, so basically these kind of that. Okay, so yeah. So these kind of field theories, my phi can be decomposed as such. This thing looks very similar, I hope, at least to some people. It looks like an inverse Fourier transform, right? Yeah, so I can split it into multiple independent parts. I can basically split the field into multiple parts, Fourier separate them, and each of the part is independent of the other part, and then its dynamics evolve completely independent of the other parts. Now you can ask a question like, why do I use e power, why do you use that specific thing as my basis for expanding? Why do you think I use e power IPX as a basis for doing this expansion? Why can't I use something else? Why do you think, what's the significance of e power IPX? Why is that the basis here? In some, yeah, okay. Okay, so if you are, okay, so it's given as a homework to you guys, just figure it out why I use that as my basis to expand this. Yeah, so I'm not going to be talking about that, but yeah, so basically I can do that, and then that thing is a solution for the differential equation that I have shown here. Now this thing, if you look closely, is just my simple harmonic oscillators, PD, OD, whatever. So what I'm trying to say here is field theories whose degrees of freedom evolve independently of other degrees of freedom, or free field theories, are equivalent to having uncountably infinite harmonic oscillators at each point associated to each degree of freedom. These two are equivalent pictures is what I am trying to say. Now I want to quantize my field, my classical field. This is a classical field, let's say. I can just quantize. So quantizing field is equivalent to quantizing a free field is equivalent to quantizing all such harmonic oscillators, right? So quantizing harmonic oscillators is easier than quantizing these fields. So I can just quantize these fields and just expand them and quantize each of the individual components. Now after doing some trivial math of just 4 pages, you end up with this phi of x. You have basically quantized my phi of x, phi. Now what are A and A dagger? It's a good question. I'll just say what they are so that you can look it up later in Google or whatever. A dagger, A plus is called my creation operator. A is called my annihilation operator. Just search. It's not a lecture on QM or QM, so just look it up, I guess. So substituting that in that Hamiltonian, basically I get this simple expression. Now this thing has a Dirac delta in it. If I put x equal to 0, what happens in this? I have a Dirac delta, x equal to 0, centered at 0, delta of x. If I put x equal to 0, what happens? Spikes to infinity. This integral does not make any sense. But I know in quantum mechanics, harmonic oscillators have something called a ground state energy. Like in better words, in 1D case, let's say this is for 1D, n equal to 0 at ground state, I have a non-zero energy for my quantized harmonic oscillator. Now feels like this thing sprouts some bullshit that does not align with this, because I have shown that these two are equivalent in some sense. Like, you can consider they are equivalent. So how do I fix this, or where does this infinity come from? I have made some assumptions while doing this, constructing such a theory. So like they are trivial assumptions, or they might look like trivial assumptions that you can make, but they are the cause of such bullshit results that I get from my QFT, at least in this case. So where do you think this infinity comes from? What assumption that I made caused this infinity to come? Or yeah, so basically one assumption I made was that, like when I was talking about fields, that my fields are spread throughout my whole space-time continuum, which basically looks like I have, like, in a very layman sense, I have a fixed value for energy at a point associated to a field. Let's say the energy is constant at each point. Now if I have such a quantity associated with infinite such points, still I would not get a finite value for energy, right? This is a very dubious thing to, or it's not a very rigorous thing to say, but yeah. So one cause of such infinity here is that I assumed my field to be spread through whole, and then I'm trying to calculate my energy of my field spread through my whole space-time continuum. Now you can be like, bro, just put a box, look at fields associated only with a small volume, try to calculate its energy, still you will get, I'm just giving you the answer, you will get bullshit results such as this, because my infinity in this case does not just come from that assumption or thing that I took to be true when I built my theory. There's another assumption that I took while doing such things, while doing this. So the other assumption is that this notion of fields, or this concept of fields itself, hold true for arbitrarily small length scales, let's say, arbitrarily small scales. Now this might, so the same argument that I gave here, let's say I go to arbitrarily small scales, and then for each point or whatever I have a energy, constant energy value associated to it, and then since I'm saying this thing holds in all, it holds to arbitrarily small length scales, I still have infinite such points, whatever, right? So I will still end up with an infinity due to this assumption. Now this basically, okay, so what I'm trying to say here is that you have to consider such theories only in certain limited scales. Now yeah, so this brings us to the concept of renormalization, or the mathematical way in which you treat these infinities by assuming that they are not true for all scales, breaking scale invariance in some sense. Yeah, so Asim will take over and discuss about renormalization and how we fix this stuff. Yes.
Am I audible? Yes, I am. I hope you guys had a lot of fun in the last section, unlike some of you who were following their sleep schedule. So let me bring the slides. Is it clear? This is an XKCD cartoon which gives you an idea of the reductionist approach to science. What do? We are trying to understand the universe. and we keep going on smaller and smaller scales to particles, and then we came to fields, as they are the more fundamental mathematical formalism appropriate to define our universe. Yes, I hope I'm not offending by saying chemistry is just applied physics. So in principle, you can just take Heisenberg equation, Schrodinger equation out of physics and apply it to a bunch of electrons, and it's the entire chemistry. So theoretically, let's say you have a nucleus where 27 electrons are dancing around it, and what's the simplest question you could ask about that? Its color. What is the color of a sample where 27 electrons, which is not a large number, are orbiting around a nucleus? Theoretically, you can just take Schrodinger equation and apply it to that sample and you can get the color. But it takes a hell out of you, and then you say, we can't. That's where chemists get their job. And yes, some people say that philosophers who are trying to understand the purpose of universe, if they talk to physicists, then they might fill in the gaps, but it's nonsense, because there are different level of emergences in between, and it is a very huge computational process to fill in those gaps. Okay, let him do his work. Can I get my slides back? So we will start with some story. So the photo you saw where there was a sphere and a light ray shining around, that is what physicists called Compton scattering, and normal people say it looking at things. So if you think classically, whenever matter is interacting with light, then out of simple trivial geometrical calculations you can predict where that light ray will bounce off. But when you come to quantum mechanics, something weird happens. That is understood through quantum electrodynamics, the science where we try to understand matter and particle interaction. And Feynman, someone named Feynman, introduced something called as Feynman diagrams, which gives you a quantified description of how particles and light interact. I will show you some examples of Feynman diagrams. These are some Feynman diagrams. Let's say we are trying to model one electron which is interacting with light. Now in quantum mechanics, anything that can happen will happen, but there will be a probability associated to it. So any matter particle interaction can be modeled by a series. So the first order term you are seeing here, where one photon is coming, it is getting absorbed by this particle, which let's take it to be electron, and it can be any particle in the standard model of particle physics shown before. And this photon bounces off again at some point in space. Now the probability of this case to happen comes out to be alpha. First of all, what is alpha? The first letter in Greek alphabet. Okay, here alpha means fine structure constant, which has a value of 1 by 137. However, as the name suggests, fine structure constant, it's not at all constant. but the scale we are using it in, it has a constant value of 1 by 137. The probability of this event to happen is alpha to the power number of vertices. What is the number of vertices in this diagram? 2. So probability will be alpha to the power 2, which is a finite number. And experimental observations very much agree to these probabilistic values. But as I said, any matter particle interaction can be expanded in terms of these kind of series, where you have one photon, you might have two photons, you might have more photons. So as the number of photons varies, the number of vertices will also vary. In those cases where probability is alpha to the power 2, you have only this diagram. But in a case where probability is alpha to the power 4, how many vertices do you need? 4. How can I have 4 vertices in this diagram? What is add one more photon. Let's add it here. Can I add it somewhere else? It will give us a different diagram. Now, without changing the number of vertices, can I add one more photon in this diagram? This is an elegant question you should think about. Yeah, answer.
Take the same 2 points.
Yes, keeping the number of vertices constant, you just add another photon here. The number of vertices is only 4. The probability associated to this diagram will be alpha to the power 4, but the diagram is different. So number of possible diagrams where the probability will be alpha to the power 4 can be infinite, because you can add more photons onto it. This was another way of getting the infinity, how we got the infinity for ground state energy in the last section, if you remember, if you were not sleeping then. Now this problem of infinity, how do we deal with it? Renormalization. And that's why this RG is there, not just to give you bad feelings. RG stands for renormalization groups. And how do we deal with this infinity? In the last section, someone, Nanta, mentioned infinity minus infinity equals finite. There are 2 kinds of infinities. Well, there was someone named Feynman. Let's see what was his opinion about this. You can read it up. Basically, what he is trying to say is this process of subtracting one infinity from another infinity is sus. But at the same time, it makes some sense. How many of you here have heard of Kenneth Wilson? Okay, how many of you here who have not done QFT have heard of Kenneth Wilson? No one. And he has done arguably the most important discovery in past half a century. And we will try to gain an idea of where did he get the intuition of discovering those renormalization groups from. We all see this boiling water in our daily life, and how did this boiling water sample led to the discovery of renormalization group? So, have you seen this diagram before? So if you have any element, any sample, anything, you heat it up when it becomes gas, and then you crank up the pressure. There comes a point where it is existing at both liquidus and in both vaporous state, right? Now if you try to look the molecular behavior at that state, that's called critical phase if I'm not wrong, then there is this mystery of infinity hiding, and we will look at it. So the next slide contains 3 square boxes where all the white space has been depicted as vapor molecules, and the black space is liquidus molecules. In the first square box, we have a gaseous sample. We took a photo of it and we are zooming it out. Let's see what happens. This is the vaporous sample. Now it's entirely vapor when you're looking at it from far away. This is the liquidus sample which is currently being zoomed out. And this is that critical phase. Which is not at all changing its picture. So this is a self-repeating fractal pattern, and surprisingly, if you take any element in the periodic table, you heat it up, you crank up the pressure, at the critical point, when you perform the same experiment, you look at their molecular orientation, you get the same fractal pattern. Any single element. Not only this, if you have a magnet, and in this picture the white parts are spin up and black is a depiction of spin down. You all know that when we heat any magnet, then at some point its magnetization capability, the magnet starts losing the magnetization capability. Now at that point where this magnetic loss happens, this picture takes the shape of the same fractal. So there's something universal about it. That's why this section, the renormalization, it's not only about particle physics. There are people trying to understand how bird flocks, in what pattern. There are people working in particle accelerator. There are people, yes, there are a lot of people. There are people trying to understand quantum field theory. And everywhere, not everywhere, at many of these places, this infinity emerges. And how do we deal with it? Renormalization group. What is renormalization group? We subtract that infinity from another infinity. Not offending mathematicians, but there's some rigorous process to it. And I was hoping some questions about why this probability is alpha, where does this alpha come from, and why the probability is alpha to the power number of vertices. So the answer to those questions has been attached. I will send it in a WhatsApp group named Astrofiles. The link to that group will be there. You can scan it. at the last page of this presentation. Now, again RG comes. Now, I'll ask you a simple question and I expect an answer. If you have a boiling water sample exactly at 100 degrees Celsius at atmospheric temperature, and I ask you what is the probability that it is close to water at 100 degrees Celsius, what can be the range of this probability? Anyone? So you in one side you have liquid at 100 degrees Celsius, in one side you have gas at 100 degrees Celsius, or this is a water sample, and in between you have that critical state. What can be the probability that your sample is close to gas or close to liquid? What will be the range of those probabilities? Yes, it will be 0 to 1. But here, if you try to naively calculate it, so as you saw, I was zooming out the picture and I was getting the same pattern. So there are liquid droplets inside of bubbles, inside of liquid droplets, inside of bubbles. And this pattern is going on further. But there must be some limit to it. There must be a point where at the lower cap atoms will start coming into the picture, and this liquid droplet and vapor bubbles will go out of the picture. That is essentially what renormalization group does. It sets a lower cap and an upper cap. This lower cap in standard model of particle physics is called UV cutoff. So any law you have in particle physics, if you try to apply it lower than that UV cutoff scale, your laws will start failing. And this probability that you are getting here, infinity, is simply wrong, isn't it? How can it be possible? So how do we deal with it? We stop being naive and then we fix a lower limit and an upper limit to our scales where infinity gets out of picture. As in last section there was mentioned something like there are two kinds of infinities and the subtraction gives us a finite number. Well, that sounds a little sus, but this was the idea we tried to motivate in the session. The renormalization, it's applicable in various areas of physics, and yes, I tried to make you feel this iffy feeling. How is this probability coming out to be infinite? And that's all. Thank you for listening. Yes, I'm expecting some claps. Nanta, can you please come on stage? Abhishek will click a group picture.